Good afternoon, everyone. This is Arun from Midas, and before moving on with the presentation, we'll quickly go over uh, with the company's introduction because most of our attendees are joining us for the first time, so would like to introduce ourselves to them. So these webinar series is brought to you by Midas Soft. The headquarters of these uh, company is based out of Seoul, South Korea. The company was established in 1989 and has 450 bridge engineers working with us. This is our worldwide existence. You can see we have 4 main branch offices in different parts of the world. We have main branch in Seoul, South Korea, then Beijing, China, then in Mumbai, India, and in New York in USA. And from this New York office we do the technical support for the software for entire North America. Along with these 4 main branch offices, we have 25 resellers in different parts of the world so that we can reach out to areas where we don't have the branches, and more than 100 different companies use Midas software. Our existing client list includes several DOTs, as you can see on the top left hand corner. The DOTs like Oregon Department of Transportation, Caltrans, Florida Department of Transportation, British Columbia Ministry of Transportation, Ministry of Transportation Ontario, Oklahoma, PennDOT. They all have Midas licenses. And if you see some main and big engineering companies like CH2M Hill, URS, Parsons Brinckerhoff, HNTB, Delcan, AECOM, Associated Engineering, Arup, Michael Baker are our main users. This is just the partial list of our existing clientele, so there are many more. Sorry if I've missed out on a few names like I can see some engineers from MMM Group that are here with us, so welcome all. So we are working hard every day to provide customized technical support to all our companies and our users so that they have a good experience with us. Along with the software, we have the softwares that are geared towards different engineering fields. So today we are the biggest computer-aided engineering company in the world. For geotechnical applications, we have Midas GTS. For building and general structure applications, we have Midas Gen. For bridges and other civil structures, we have Midas Civil. And for advanced nonlinear structure analysis, we have Midas FEA. And for mechanical engineering, we have Midas NFX. So today's presentation is directed towards the application of Midas Civil in some of the signature structures that our engineer from Michael Baker has done. So Daniel will be talking more about what features and how he handled his project. With software, we also provide online support and training to all our engineers. They are free to join in the training sessions that we conduct periodically. We also do several offline seminars, and these are some shots from the bridge seminar that we did in New York last year. We conduct similar conferences and seminars in different parts of the world. We have taken these seminars online these days. So we have online technical seminar where you can see we invite professors from different universities, engineers from different companies, and DoD professionals to share their experience, their past case studies, their research work, their technical papers with everyone. And all these lecture sessions, recordings, and presentations are shared on our website, which is dedicated for enhanced or continued learning. So this website is called www.goodengineers.com. Currently it is under development because we are updating the recent webinar series that we concluded. So once it's back up and running, you will be able to see all the lectures updated. Now I'll quickly go over the enhancements in the Midas Civil version 2013. The graphical user interface has been modified and updated with the ribbon interface, and this has been done to make more efficient utilization of the workspace you have. You will have multiple tree menus so that you can select certain elements from one tree menu and apply the loading from the other. You can also split screen into a number of windows so you can see and focus on different parts of the bridges simultaneously. And through this enhanced ribbon menu interface, we have reduced the number of clicks that you have to make to reach to your required function. Then we have also updated the design codes for pre-stressed concrete design as per AASHTO LRFD 2012 and as per Canadian standards 2010. And our major update includes the updation of reports. In these reports, you will have not only just the calculation values and the cross-section capacities, but also it will mention all the clauses that it has considered for doing this design check, and if certain clause is checked and it is not good, then it will report it right here as well. So it's a detailed report in addition to the graphical report that you can view at any point of time. AASHTO LRFD 2012 moving load code has been updated, so is our software. So with the updations in the code, we have updated the software as well. Now in AASHTO LRFD, you will be able to apply any kind of standard truck or tandem vehicle along with the permit truck simultaneously. And this permit truck will allow you to define any kind of axle arrangements and wheel arrangements under these axles in a symmetric or asymmetric vehicle. Same things have been pulled out and applied in Canadian standards as well. Earlier the software used to include the dynamic load allowance automatically, but now we have given the control to user as well as to the software. So if engineers wants to apply the dynamic load allowance themselves, they can control that as well. And we have also brought in permit vehicles as per BCMOT and as well as user-defined permit vehicles for Canadian standards as well. The software has been enhanced to do the load rating as well as per 2012 LRFR. And the general section designer has been updated for both AASHTO LRFD ACI as well as for Canadian standards. So this particular feature will allow you to generate stress contours in concrete as well as rebar and steel, and it will also generate the moment curvature diagrams and the PMM interaction diagrams in both 2D and 3D. It will also check whether the section is safe or not. Another development has been done for grillage model wizard, where you can consider any kind of tapered and flared girder arrangement. And the biggest development of this release is the rail track analysis wizard. Now this particular feature will allow you to define any kind of rail loading onto the structure or train loading onto the structure. It will model your non-linear ballast links automatically. It will do the thermal analysis, the braking analysis, acceleration analysis for the train, for the track and the structure. And you can simulate it through a construction staging and without construction staging as well. So this will in true sense deliver you the capability or the strength of handling any kind of light rail project or heavy or freight train truck or train project. Then we have enhancements for multilinear links that can be used for inelastic and nonlinear time history analysis. You can apply different type of soil springs you want and simulate the seismic analysis, including displacement time history. And you can also generate moment curvature interactions. We have included the Meanders model and the Kenton Park model for concrete, and multilinear curve for steel for generating these moment curvature diagrams within the software itself. So this is the summary of the developments that you have gone through. There are a couple of more, but I'll not hold you any longer, and I'll give the control back to Puya, and then we'll be over to Daniel for the presentation. I hope you enjoy the presentation today, and if you have any questions, feel free to contact us. Thank you.
All right, thanks to Arun, and now time to back to the presentation. And before we start the presentation, let me quickly go through background of Daniel. Daniel is actually working as a senior bridge engineer in Michael Baker in Cleveland, and he got his Bachelor of Art in Physics in Carleton College, and he got his Bachelor and Master in Structural Engineering from the Washington University of St. Louis. And now he's been working on several projects, and he has an extensive experience. And today he will be talking about 3D model of the trusses and arch bridges. So I will give the control to Daniel, and he will start the presentation. But before that, please just, if you have any question, feel free to use this question and chat option and send the question to us. We'll try to answer the questions either after the presentation or during the presentation if it's required. Thank you, and I will. Okay, Daniel, you may start the presentation.
Well, thank you, Puya, for the introduction, and thanks everyone for tuning in. Computer structural analysis methods incorporating 3D modeling have seen significant increases in usage for bridge design and rehabilitation projects. 3D modeling can give insights into structural behavior that might not be apparent from 2D analysis methods. With 3D modeling, however, comes an increase in modeling complexity and the computer analysis runtime required to produce results. Three-dimensional computer analysis models of complex bridges can take weeks to develop, even with the sophisticated graphical interfaces of today's structural analysis programs. The computer runtimes of 3D models also tend to be much longer than those of 2D models, the runtimes of 6 to 24 hours being typical, in my experience, for large bridges. Trying to advance the slide. Okay, here we go. While the benefits of 3D modeling are well known for heavily skewed or curved bridges, they are less well established for straight truss and arch bridges of moderate to long spans. It has been my experience that, in general, 3D modeling has proved most beneficial for analysis of structure widening, interaction between main load-carrying members in the floor system, floor beam end moments, and geometric nonlinear effects caused by lateral loads and truss and arch structures. Two-dimensional structural analysis methods have proved sufficient for determining forces in main truss and arch members due to vertical loads. These observations are the result of experience from the Innerbelt Bridge deck truss rehabilitation project in Cleveland, Ohio, the Milton Madison Bridge through truss replacement over the Ohio River between Indiana and Kentucky, and the Hastings Bridge replacement in Minnesota. A common feature of all three projects is that these bridges make use of structural forms that deviate from those traditionally used for truss and arch structures. And by traditional structural forms, I mean a configuration where basically the whole structure can be analyzed as just a series of 2D models with, say, simply supported stringers or stringers continuous over only a few spans, resting on floor beams that can be considered to be pinned on at their ends, that are then supported by either two planar trusses or arches where the whole thing lends itself to a 2D analysis. These three bridges are different, though, and don't really lend themselves to that type of simplified analysis. The Inner-Belt Bridge included the complex widening structure. The Milton-Madison Bridge has less sway bracing than is typical and an unconventional floor system. And the Hastings Bridge also uses an unconventional floor system and has no lateral bracing between the arches. These departures from standard practice call for a more practical, more thorough analysis than is practical using 2D modeling. For the past 100 years, truss bridges have commonly been analyzed using planar two-dimensional structural analysis methods. These methods have been proven satisfactory for most truss structures. Cleveland's Inner-Belt Bridge, however, has a structural configuration that is different from most other truss bridges. Located near downtown Cleveland, the Inner-Belt Bridge is a 9-span, 3,000-foot-long, variable depth deck truss that carries Interstate 90 across the Cuyahoga River Valley. The 8-lane bridge functions as a major artery for traffic traveling to downtown Cleveland from both the south and west, and for through traffic on Interstate 90. The bridge is the widest ever built in the state of Ohio and was opened on August 15, 1959. Looking at an elevation view, see the bridge consists of alternating statically determinate, cantilever, and suspended spans. The existing structure has an out-to-out width of approximately 116 feet and is supported by two main trusses with a center-to-center spacing of approximately 90 feet. Transverse floor trusses span between the main trusses at panel points, which are spaced at 25 feet. In spans 4 through 8, the bridge is horizontally curved. And of particular interest is the winding structure that was added to the west end of the bridge in the early 1980s. This structure extended the length of an on-ramp from Cleveland's Tremont neighborhood, and in its configuration, which I'm about to show, is quite different than a traditional truss structure would be. Looking at an elevation view of the winding structure essentially consisted of a pretty large and deep steel plate girder that was supported by 5 diagonal struts that framed into the bottom chord of the south truss of the bridge in units 1 and 2. Looking at an isometric view of the winding structure, this plate girder was also connected to the existing truss through a series of floor beam extensions that branched off from the ends of the existing floor beams of the truss. And then additional stringers were then placed perpendicular to the floor beam extensions to create the widened deck area. But between this girder and the various struts and floor beam extensions, this was a fairly indeterminate structure and one whose load distribution into the existing truss was not straightforward. Well, in addition to the winding structure, another feature in which this bridge differed from most trusses is the presence of significant bending moments in a few of the truss members. And just as a refresher, these so-called primary bending forces in truss terminology develop when a load is applied to a truss member away from a panel point or joint. And in this just simple truss right here, member AB would have to develop a bending moment to carry this force F which is applied, since force F is not applied at a joint of the truss. And in the truss, Inner-Belt Bridge truss, primary moments developed in the panels adjacent to joints between the suspended units and the cantilever units due to non-standard geometry in these panels. Looking a little bit more closely at the detail of the end panel of the cantilever span, see that point A, and looking at the joint between the lower chord and the diagonal and the vertical, see that point A is the work point of the vertical and floor truss connection to the lower chord, while point B is the work point of the diagonal and I-bar connection to the lower chord. These points are offset by 3 feet, which may not seem like much, but when you consider the magnitude of the loads involved, is enough to generate significant primary moments in the truss. And, well, in addition to the winding structure and these moments, a third unusual factor of this bridge was that the west bank of the Cuyahoga River, on which supports units 1 and 2, is slowly moving to the east. But it's been moving to the east fast enough due to an unstable slope that units 1 and 2, well, Unit 2 during the summer months had begun, the south truss of Unit 2 during the summer months had started to come into contact with Unit 3 due to these slope movements. And as during the summer, due to thermal expansion, this would cause the units to come into contact, which then would induce a force into the south truss of Unit 3. Well, by 2008, the condition of the entire bridge had deteriorated, and there were significant portions of the bridge with significant section loss. The Ohio Department of Transportation hired Richland Engineering Limited to design a major rehabilitation on a fast-track schedule due to the significant deterioration. Michael Baker Jr. was engaged as a subconsultant to Richland for modeling, main truss member load rating, and construction stage analysis. Well, Baker elected to model the bridge and to make a 3D model of the bridge due to a number of the factors that made this bridge different than most truss bridges. For one was the widening structure, which, as I've mentioned before, was a very complex structure whose load distribution into the existing truss was not straightforward. Another was that this truss included horizontal curvature and was unusually wide, and there was some question as to whether the traditional 2D planar analysis methods for trusses would really be applicable to a bridge that was this wide and had horizontal curvature. Another factor were the presence of those primary moments that I mentioned, and also the analysis of what those thermal forces did when in the existing truss, that when Unit 2 came into contact to Unit 3 during the hot summer months. So given all these, when considering all these factors together, it really seemed best to make a 3D model of the truss, since given these unusual factors, it really wasn't clear if 2D analysis methods applied. And Midas Civil software was used to perform the analysis. Well, for the 3D model, the main truss, floor beam, stringer, and winding structure plate girder members were modeled using beam elements. Shell elements were used to model the deck, and the deck in each unit was modeled as a floating system using rigid links, with longitudinal restraint at one end only to prevent composite action with the stringers, since the stringers were designed to be non-composite. Live loads were applied to the model using surface lanes defined on the shell element deck. The model had about 20,000 elements and had a runtime of about 6 hours. Main truss member axial force results from the Baker 3D model were compared with the results of a previous load rating performed using 2D analysis methods and the forces shown on the 1950s era bridge plans, which are most likely also the results of a 2D analysis. Close agreement was found between the forces produced from all three analyses, but away from the joints between units where there were primary moments and away from the widening structure. So this analysis showed that 3D modeling probably did not result in a significantly more accurate prediction of truss axial forces that would be obtained from a 2D analysis for the regions of the bridge that were away from the widening structure and away from the end panels. So this comparison really showed that even for a truss with an unusually wide width and horizontal curvature, or at least mild horizontal curvature in this case, the 2D analysis methods were really still applicable for that, but not necessarily for the analysis of the widening structure or the primary moments. And although the 3D analysis results included transverse bending moments in the truss members, saw from this comparison and from the rating that the contributions of these moments to the demand capacity ratios of the truss members were small. Well, after going through a lot of number crunching for the rating of this bridge and processing these results, it was found that many of the members and gusset plates with the highest demand to capacity ratios were located in the south truss adjacent to the winding structure. The controlling member of the load rating was a bottom chord member of the south truss located at the east end of the winding structure. Located in the bottom chord of the south truss in the west end of Unit 3, this member was designated L300 L301S. The low operating rating of this member, which was 73% for the governing Ohio legal loading, was due to a combination of factors. One was deterioration in this member since it was located near an expansion joint. Another one was that this member was carrying a decent amount more force than it was originally designed for due to the presence of the winding structure. A third was that this member being in the bottom chord of an end span of an end panel adjacent to a joint between an adjacent unit was also subject to a significant primary bending moment. So when all of these factors were combined together, the deterioration, the load above the original design load due to the winding structure, and the primary bending moment, this member didn't have sufficient capacity to meet its operating rating. Now that 73% did not include the effects of the Unit 2 coming into contact with Unit 3. As you can see from the right picture here, this member was located at the panel where Unit 2 in the summer months was touching Unit 3 due to those slope movements. And when you consider the application of the force due to these units coming into contact as temperatures rise, this induced an additional moment into L300 L301S due to the eccentricity of the location of this, the eccentricity between the location of where this force is applied and the center line of the member. And when this force was combined with the dead load and live load forces used for the operating rating, the bridge was shown to have a far reduced load carrying capacity even below the 73% operating rating. Well, the Ohio Department of Transportation had requested that a calibration of the model not be done during the development of the model, but upon seeing these results, they were curious to see just how closely this 3D model that we had made actually reflected reality. And so the controlling member, as long as together with a few others, were instrumented with strain gauges, and trucks of a known weight were run across the bridge and placed at designated locations, and the strains were compared to the forces predicted by the model. This plot here on the horizontal axis shows height from the base of the bottom flange plate of L300 L301S, while strains are on the vertical axis. You can see that the comparison of the best fit of the predicted and actual strains, while not exact, was pretty close. And one important thing to see here is that there was, as the model predicted, a significant bending moment in this member. If this member had just been under axial force, which is commonly the assumption for truss members, the strain should be constant from the bottom to the top of the member. But as you can see that it's increasing here towards the top, that shows that there is a significant bending moment in the member as well. Well, once the Ohio Department of Transportation saw these results that L300 L301S had such a low operating rating, and that many of the other worst performing members of the truss were located adjacent to the winding structure and seemed to be performing poorly, partly due to the additional load of the winding structure, ODOT decided to remove the winding structure to lower the load on these poor performing members. removal was undertaken during 2009, and here's a photo of the removal underway. And also the decision was made to pick up Units 1 and 2, which was, I've mentioned, were running into Unit 3 due to the slope movements, and move them west away from Unit 3 4 inches. So over Memorial Day 2009, the bridge was closed to traffic. Units 1 and 2 were picked up with hydraulic jacks and moved to the west 4 inches and set back down again. And as part of this procedure, we had to do a fair amount of additional analysis using the 3D model to see what the effects of friction of the I-bars between units would be due to there likely being some resistance to movement during this jacking and moving process. But everything went well, and now the Unit 2 and Unit 3 are no longer in contact. Here's a photo of the bridge now. You can see that the winding structure has been removed. And by contrast, here's a photo of how the bridge appeared when the winding structure was still in place. Well, in terms of what we could conclude from this project, it really seemed that the presence of structural features on this bridge that are not typical for trusses and do not fit the perimeters typically used for truss analysis, which would be, say, a planar array of triangulated pin-connected members, that really get you, that since these things did not hold with the winding structure being there, it really did make sense to use the 3D model to model the bridge. We also saw that the effects of primary bending moments were quite significant with regards to the load rating, and are something that should be considered in future ratings of truss bridges. So even if there is an offset of just 3 feet between different parts of a connection of a truss, it should still be included in the structural model. We saw that the effects of thermal forces due to the units coming into contact, due to substructure movements, were quite significant and really should be considered in the analysis. But we also saw that for regions of the truss away from the winding structure, which of course is not typical for trusses, and away from these unusual end connection details, that the results from the 3D and 2D analysis were extremely similar, leading me to conclude at least that for trusses that do fit traditional assumptions, that a 2D analysis of the main members really should be sufficient. But at the same time, for a very unusual truss such as this, a 3D model and analysis is preferred. Well, on to the Milton-Madison Bridge. The availability of 3D computer analysis methods does allow for innovative designs that depart from past practice, which is the case for the design of the new Milton-Madison through truss bridge over the Ohio River. The existing Milton-Madison Bridge is also a through truss, which was completed in 1929 and which spans the Ohio River between Milton, Kentucky and Madison, Indiana. Here's a map showing the location of the project site on the Ohio River. You can see that it's really one of the only crossings located on the river between Louisville, Kentucky and Cincinnati, Ohio. The maximum span of the bridge is 727 feet, 3 inches. Due to deterioration of the bridge and substandard roadway widths, the Indiana Department of Transportation engaged Baker to conduct a bridge replacement study. The preference of the communities in which the bridge was located was for a replacement structure that was also a through truss, with an appearance similar to that of the original bridge. We determined that the piers of the original bridge could be used to support the replacement through truss, provided that the piers were strengthened first. Baker undertook a preliminary design of the replacement superstructure to determine probable design loads on the piers. The model used for preliminary design of the replacement truss, we utilized a two-dimensional model of the main truss members to obtain dead load and live loads, and a three-dimensional model of the truss to obtain wind loads. We used conventional lever rule calculations to determine dead load and live load distribution factors for the 2D truss model. The preliminary design also followed the traditional AASHTO requirement for the inclusion of sway bracing 5 feet or more deep at each intermediate panel point for through truss span.
Okay, I just figured out how to view the questions people are sending me. One question is, can you comment on deck rebar for skewed bridges? Generally, I believe that the number, the cutoff is something like 10 degrees. ODOT recommends turning that 90 degrees to the girders, just because your spans start to get very long if you skew the rebar on a heavy skew. You also don't want to get the two maps of rebar that close to parallel to each other. Question is, how do you actually measure the twist using computer FE analysis such as Midas? You can't get, there are many methods in Midas. You can get measured node rotations in Midas. You can also, if you have a multiple node element like a plate element girder, you can look at deflections between nodes in that element to measure the deflections. Like if you're looking at the slope of the web, you can take the top and bottom node of the web and get a differential slope between those two. What type of connection between the cross frames and the girders is used in the FE model? We're using a rigid link between the cross frame elements and the girders. If you go to a really detailed plate element model, you could directly connect those, or you could put in the intermediate stiffeners and connect those directly to the cross frames. We've never gone that detailed, generally for design purposes. Generally, it's a rigid link between generally the flange node directly to the truss element. In the 2D grid model with truss bracing, how did the offset of the brace form the center line of beam is modeled? Oh, that's that again. So it's talking about the 2D grid model with the truss bracing. We used rigid links between the girder elements and the truss members to model that link. So we just assume that the stiffeners there provide a rigid connection. Question, is the presentation available for download? I believe Midas is going to put that up. If they don't and you want to have it, email me and I can get it to you. There's a question about integral end bends on skewed bridges, and yes, that an integral end bent is basically an end cross frame, except it's much more stiff. So the same policy applies, that for a heavily skewed bridge, you would leave that unpoured until after the deck pour, because that will restrain those girders at the end and force them to twist just beyond the end bent if it's in place, and it'll put very high stresses in the flanges. Question about shell elements. For the purpose of what we're doing, a shell element and a thick plate element would be the same thing. It's just an element that can take bending along with in-plane forces. And it's probably the most appropriate thing to model a web action in a girder. There's a question about AASHTO recommending a 10 KSI allowance for flange lateral bending. I think that's if you have staggered cross frames. I'm not sure exactly what provision of the code you're talking about, but I think as long as your cross frames are in line across the width of the bridge, you don't need to consider that. I'm not sure if that's in the current AASHTO code, but I know that that was there at some point, that you put an allowance when you have staggered cross frames. You need to make an allowance for flange bending if you're not doing a detailed analysis. Then there's a question about staggering the diaphragms rather than having diaphragms in each bay. And yeah, I know there is a school of thought that there are advantages to that. It does put more bending in the flanges because you're forcing, that torsion into the flanges. It does soften up your cross-frame connections. If you were going to do that, I would recommend that you do a model including the including elements for the flanges, a 3D model of some sort, and look at that lateral bending stress. Question is the method of detailing the diaphragm fit placed on the plans in Ohio. It's in their material specs for steel girders. By default, it is steel dead load fit. If it's going to be anything other, there needs to be a plan note stating that. That's all the questions I'm seeing so far. If you do want me to send you the presentation, my email again is travis.butts. Here it is right here. travis.butts@purchaseniple.com. Feel free to contact me with any questions, or I can send you the presentation.
All right, Travis, thank you again for answering the questions. So please send us, if you have any more questions, to Travis, or send it to our email at midasoft@midasuser.com. We will be sharing the recording in a couple of hours, and if you want the presentation files, you can also contact Travis. And thank you so much, everybody, and you have a great day. I will be ending this session and waiting for your emails. Thank you. Bye.
Fatigue limit state design. The floor beam negative moments were largest near midspan of the longest truss span. This effect likely becomes more significant as truss spans increase in length and would have been difficult to find without 3D modeling. So what's going on in this image here is that these are moment diagrams of the floor beams for the longest truss span with relative deflections which are amplified shown. And the negative moments are the tails of these moment diagrams towards their ends. And zooming in on two of those, which appear on the next slide, one can see that for a moment diagram near support, the maximum magnitude of this factored load is about 788 kip feet. While if you zoom in on a moment diagram near the center of the span, the maximum magnitude has increased to 2,000 kip feet, which is pretty significant. And even though these forces are not necessary to maintain equilibrium for strength, it's still something that seemed very worthwhile to be aware of for service and fatigue design. So, and really what we learned from the Milton Madison Bridge was the importance of using consistent 2D and 3D design approaches for one. That if you use a 3D model, that's fine, but if load is shed then into secondary bracing members, those bracing members need to be designed for that load. So one has to remember to check dead loads and live loads in those bracing members, which typically may not be designed for them. And also we saw that in some cases, using a 2D model really may be the way to go for design of main members due to vertical loads, because that way one can be sure that design is conservative. But we also saw the surprising result that for a long span truss bridge with reduced bracing, that this departure from standard practice now leads to a case where 3D geometric nonlinear analysis seems to be required, at least for truss bridges of this length. And we also saw that departing from what would be a standard floor system for a truss with, say, stringers that are continuous over just only a few spans, and having stringers continuous over the whole length of the bridge, leads to effects that are really best to use a 3D model to analyze. Where by contrast, if this had been a more traditional configuration with short stringers, a series of planar analyses, 2D planar analyses, like I mentioned near the beginning of the talk, would have likely been sufficient. Now for the Hastings Bridge. Like the Milton-Madison Bridge, the new Hastings Bridge will also utilize a stringer floor beam system that departs from typical past practices. Located 20 miles southeast of St. Paul, Minnesota, the new bridge will replace an existing structure that carries U.S. Highway 61 over the Mississippi River in Hastings, Minnesota. The bridge, the 545-foot-long main span, is currently under construction by a design-build team led by Lunda Construction and Parsons Transportation Group. The project was bid for $120 million. Baker's role on the design-build team is to provide independent design review services to Parsons. The main span of the new Hastings Bridge will be an unbit braced tied arch featuring 2 arch ribs consisting of trapezoidal steel box girders and 2 cast-in-place post-tension concrete tie girders. Steel plate girder floor beams span between the tie girders. Steel stringers span between the floor beams, and the ends of each stringer are fully fixed to the floor beams. This floor system configuration allows for alternate load paths in the case of a floor beam fracture, so it allows for additional redundancy. The arch and tie girder are integrally connected to the concrete spans, which support concrete piers, which support the main span. Now, while the use of unbraced arches such as this bridge is quite unique, several aspects of the 3D behavior of the main span's floor system, however, are likely applicable to other bridges that utilize stringer floor beam systems, such as other arches and truss bridges. We created a multi-step construction 3D model of the Hastings main span as a check of the Parsons analysis results. The results of the model showed that over the course of construction, significant out-of-plane moments and deformations developed in the floor beams between the tie girders and exterior stringers. Well, what's shown here is a plot of magnified deformations of the floor system when seen in plan. And if looking at a say corner of the bridge here, you can see that there's a significant out-of-plane displacement of the floor beams between the exterior stringer and the tie girder. And looking over the length of the bridge, one can see that the magnitude of this out-of-plane displacement increases towards the end of the bridge as you move away from the center of the bridge. And the source of this behavior becomes clear once you look at a 3D view of the deformations of the bridge. And so what's happening is that the floor beams are connected, of course, at their ends to the tie girder, and due to the dead load of the deck and live load, the displacement of the floor beams is greater, as one would expect, towards midspan than at the ends of the floor beams. Now, this causes the deck towards the center to displace lower towards its center than at its edges near the tie girder. And this lower displacement, since the stringers are integrally fixed to the floor beams, causes the stringers to move with the floor beams and causes towards the end of the span there to be a differential longitudinal movement between the stringers and the tie girders, since the stringers are displacing downward farther. Now, since the stringers and the floor beams and the tie girder are all integrally fixed to one another, this causes the tie girder to have to displace out of plane between the exterior stringer and the tie girder to make up for this difference in longitudinal deformations. Now, the construction sequence was developed to minimize these force effects, but it is difficult to avoid them entirely. The stringers must be in place prior to placing the deck, and the weight of the deck causes the stringers to move downward and longitudinally with respect to the tie girder. Similar floor beam force effects could be expected to develop in truss and arch bridges in which the stringers and floor beams are integrally connected. But the structural behavior would not develop in conventional truss and arch bridges in which longitudinal stringer movements are unrestricted. But this phenomenon can develop in a conventional bridge, or with a traditional layout of the stringers and floor beams, in which connections between stringers and floor beams that allow for longitudinal stringer movements have become frozen. But for the design of the unconventional Hastings Bridge, the out-of-plane deformations of the floor beams likely only became apparent through the use of 3D modeling techniques. And I should add that these, both the Hastings Bridge and Milton Madison were also modeled in Midas Civil. Well, a large part of this project was the analysis of the lateral stability of the unbraced arches. And this analysis was really outside the scope of this talk. But I should add that using both the beam element representations of the arch in a 3D model and using element representation of the arch, which took into account its trapezoidal shape, we conducted both staged large displacement geometric nonlinear analysis with initial imperfections introduced in the structure, and also linear eigenvalue buckling analysis. In addition, we compared the results to hand calculations for this problem and found that the arch should have a factor of safety above the maximum factored loads of at least 3 for stability. So in terms from Hastings, although the lateral unbraced arches were certainly unique, what we found that we thought would be most applicable to other bridges was this out-of-plane displacement of the floor beams that I mentioned that we didn't expect to see. So this made us really think that in any other bridge that used a similar fixed floor beam stringer system to add redundancy to the floor system, that it was really best to, that would be a case in which 3D analysis would really be best, because it's an effect that can't be easily captured using 2D. And also, it's important to remember, like I mentioned, that in a more conventional bridge, if the movements of the stringers have become frozen with respect to the floor beams, this effect could be expected to develop as well. You might want to make a 3D model to look into that. Well, overall, in terms of when is 3D analysis a good bet for a project, experience gained from the Cleveland Central Viaduct or Interbelt Bridge, Milton Madison, and the Hastings Bridge projects showed that 3D structural modeling can provide valuable information for unconventional structures about transverse load distribution, lateral load resistance, and floor system behavior that would be difficult to obtain from 2D analysis techniques. So I would expect that 3D modeling would be beneficial for the analysis of transverse loads and floor systems in most medium to long span trusses and arches which, like these bridges, depart from traditional structural forms. Departures from traditional analysis methods, planar analysis methods, seem to go hand in hand with departures from the traditional forms used for these types of bridges. By contrast, there were few differences observed between 2D and 3D analyses for the predicted axial forces in main truss members. So 2D analysis methods are thus likely sufficient for designs of new bridges and load ratings of existing bridges, truss and arch bridges, that follow traditional structural configurations for the main members, floor systems, and bracing, which, as I have mentioned, would allow for the bridge to be considered as a series of planar analyses of the stringers, floor systems, and main members without having to worry about the introduction of out-of-plane force effects that are then best captured and analyzed using a 3D model. But for unconventional, innovative structures, the added complexity of 3D modeling is worthwhile for the insights it provides into structural performance that could easily be overlooked using 2D analysis. Well, I'd like to briefly acknowledge the many people, Michael Baker, who I worked on these projects with and who I learned a lot of this stuff from. And that, thank you for tuning in, and thank you, Midas, for inviting me to present. And I guess we have a few minutes, it looks like, and I'd be happy to take any questions, figure out how to do that. And also, if you would like to contact me with questions after the webinar is over, my contact information is below. Feel free to do so. So let me click on the questions box here, see what has been asked. Okay, with respect to the here's let's see, we have one question. With respect to the live load lane, does it do pattern loading for the worst effect? Yes, it certainly does. That is one advantage of even for bridge sets is the inner belt bridge with the non-composite stringers of using surface lanes on a planar surface to do the live load versus line lanes. Is it will load the whole surface in such a way, and all of the different lanes in such a way as to maximize the particular force effect that is in question. So if the force effect is something that's, say, torsional on a floor system, it will load just one side of the bridge and not the other. Or if it's a force effect that is trying to maximize negative moment, it will create a pattern loading over a series of spans to do that. Let's see. Looks like there are two more questions here. Let me look here. Okay, with respect to live load generator, can live load be swept to the edge of the lane? Well, I find the best way to deal with moving live load transversely is to just define a different series of lanes for different live loading patterns, just following the AASHTO guidelines. So, for instance, to maximize force on an exterior on a main truss member, that would be for most bridges a situation where the live load is placed as far to, say, the right of the bridge if this main truss is the right main truss. While, say, to maximize force on a center stringer, that would be a different live load pattern where, say, the lanes are then centered as close as they can be following AASHTO to the center line of the bridge. And Midas will allow you to define all of these different live load placements and configurations using different sets of lanes, which are then in different sets of moving load cases. And then after all of these moving load cases run for the different sets of lane placements, you can then take an envelope solution to show which will be the very worst. Let me try to maximize the question box here. There seem to be a number of questions. It's good. Okay. Were gusset plates included in the, okay, the next question is, were gusset plates included in the 3D models? Also, could you elaborate on boundary conditions and how those were modeled? Gusset plates were not included in the 3D models. We went through, I didn't want to get into it here because it was quite extensive, quite a long comparison process between using fixed end conditions for the truss members, pin-ended conditions, or including, say, fixed end conditions with a member offset to reflect the added stiffness of the gusset plate. This the inner belt bridge analysis took place mostly in 2008, which was right after that was right in the aftermath of the 35W collapse, and the Ohio Department of Transportation and Baker were being pretty cautious about the analysis. So ODOT, the Ohio Department of Transportation, elected to go for a fixed connection analysis. And we discovered using a fixed connection analysis induces what are termed secondary moments, primarily in the ends of the truss members, due to restrained deformations of the members as the truss deflects downwards. And to avoid an overly conservative analysis, we had to take into account moments that were induced in the truss by secondary moments that were induced in the truss during the fabrication and erection process, which are opposite in nature to the secondary moments induced by dead load deflections. And we also had to be careful with using the C, equivalent moment factor in the standard specifications to avoid an overly conservative analysis. But when we did that for the fixed condition analysis, it actually ends up that the results between that and the pin condition analysis end up being pretty close. And with respect to secondary moments and trusses, I should mention too that these moments, which are due to the restrained end conditions, fixed end conditions, as yielding begins due to these moments, then the restraint due to this yielding decreases, and the yielding spreads over more of the member. So what you have at the end at the strength limit state is more of the pin condition that you end up designing for anyway. So although fixed end conditions were used for this analysis, it would have still been valid, and we would have likely gotten much the same results if we used pin end conditions. The next question is, did you perform seismic analysis? Yes, for Milton, Madison, and Hastings. No, for the Innerbelt Bridge, because that was outside of the scope of the project, and Ohio is quite a low seismic zone, and we used 3D response spectrum analysis for both of those bridges, which were, I believe, I think designed for seismic zone B. So it wasn't terribly large seismic zone, so we didn't have to get any more complicated than that. But we did perform a 3D seismic analysis for those two bridges. The next question is, how do you get rid of out-of-plane deformations of floor beams at the end? Do you release the stringers at floor beam connections? So yes, those out-of-plane deformations of the stringers can't be out of the floor beams, excuse me, can't be eliminated entirely because live load will cause them, and at some point, I mean, the deck has to be placed at some point in time, but part of the construction sequence that was developed to minimize these displacements did include installing the stringers at the end bays of their bridge after all the other stringers had been installed and after most of the deck had been poured. So staging the placement of the stringers and the pouring of the deck does reduce these out-of-plane displacements of the floor beams, and is a good technique to keep in mind for that. But unfortunately, they can't be avoided entirely and are somewhat of a side effect of using this fixed stringer floor beam system. But although the effect is undesirable, the benefit of this is that should there be some unexpected fracture or failure of the floor beam due to all these fixed connections, the floor system as a whole has a lot more redundancy, and forces can be redistributed away from the location of the floor beam fracture. The next question is, what was the weight size of the added widening member on the first bridge? I don't have the statistics for the weight and size of the added member just right at my fingertips right now. I don't want to just try to pull a number out of thin air, but if you'd like, if you send me your contact information, I can send you a PDF of the set of drawings for that widening structure in which all the dimensions and material quantities are shown. Just looks like the asker is Eric Francis Wright, so if you could send me or Midas your contact information, I will send you a PDF of the plans for the widening structure. Okay, looks like the second to last question is, what is an increase in lateral bracing forces from 3D analysis as compared to 2D analysis in the analyzed truss bridge? Well, that's a little tricky to answer. I would say that the increase in the forces in the lateral bracing would be, to start with, that the lateral bracing would traditionally most likely not be designed for any dead load or live load. It would just be designed to carry forces as part of the lateral force resisting system for wind. So by including it in the 3D analysis, it is seeing forces, significant forces from dead load and live load that would not likely be seen in its design at all. So although I don't have a percentage off the top of my head for what that increase is, I would expect it may be as high as 100%, because it's now seeing to load due to dead load and live load force effects that it wouldn't be seeing at all in a conventional design just for wind. The last question is, when you did seismic analysis, how did you model the substructure? We just sort of for Milton, Madison, we did a parametric study of how different assumptions of modeling the substructure affected the results. The was primarily primarily done to see what the loads of the what the effect of having a heavier superstructure on these existing piers would be, which were then retrofitted. And the Milton-Madison Bridge used a center fixed pier, I believe, and elastomeric bearings for the other piers, which do distribute some of the load to the other piers. So, but that seismic analysis was pretty critical as far as designing the pier retrofit, since that was that I think was the governing longitudinal load on those existing piers, as there was now a new truss bridge on them that was, quite a bit wider and heavier than the existing bridge.